And here you have it. I have right in front of you my clock system built with the 555 timer to generate pulses which will be used for a small 8-bit computer. And as we know, the 555 can be developed to produce pulses in 3 non-modes. And right here we have the LED blinking, and this is the A mode pulse, which I have the drawings here. And looking at this, you could see the LED blinking high, low, high, low, high, low. And this is really because of this 555 timer, which has 3 resistors of 5 kilo ohms each. And what's really happening here is you have this capacitor here, which is at this point the capacitor is charging because you have 5 volts coming in, and the capacitor is unable to produce charge at this time, so you have 0 volts at this point going into the comparator. But because the voltage at this point is 1.67, as we know, the 5 volts is divided into 3, so this is 1/3, this is 2/3, and then you have the 5 volt at the top. So but at this point you have 0, which is less than 1.67. Therefore the SL latch is gonna set to produce an output, and this would remain this way while the capacitor is charging. So once the capacitor charges up to produce enough volts, which is above 3.3 volts, and then you have the volt above 3.3 volt here. Therefore the reset side of the SL latch is gonna set, and which would trigger the output off, and we would have the complement of the output high, and this is going to activate this transistor, therefore allowing the capacitor to discharge to ground. And why the capacitor is discharging to ground, why the capacitor is discharging, it means once the value of the volt is equivalent to 1.6 or just goes below 1.6 volts, that it means it's become lesser than this voltage here, and therefore this comparator kicks in again and sets the SL latch, and this cycle repeats, and this is why we're having this pulse up and down. So if the capacitor is charging up to 3.3 volts, falling down to 1.67 volts, it's charging up again and coming down. And by playing around with these values, these 2 resistors, you can control the speed of the frequency of the pulse, and which is what I have here. I have the 555 timer, and here's my variable resistor. I can adjust the value to increase the pulse speed frequency, and this is the capacitor that is producing the input for the comparators to perform this pulse, and this is known as the A stable mode. And also on the breadboard I have the mono stable mode. So what this means basically, it just has one mode, it activates once and it shuts off. So we're going to see that on the oscilloscopes quite shortly. So what's really happening here is we have a switch on the trigger side. So the switch of course is connected to a pull-up resistor to provide, so we can connect this directly to provide 5 volts to the trigger. But you see, because 5 volts is much higher than 1.67 volt, therefore this set button would be off, and therefore would have no output signal, and therefore our LED light will be off. But the moment we push this button, we are going to send all these 5 volts through this switch to ground. And therefore, this trigger input would be 0 volts, which is lesser than 1.6 volts. And therefore, this comparator is going to set the SR latch. And then we're going to have an output. And this would remain this way because we have this capacitor here being charged. And while this is on, this capacitor is going to produce the charge required. Once this capacitor is charged above 3.3 volts, and therefore you have the reset button set again, and it's draining the charge back. And once this is set again, then it means our button is out, and therefore we are back to 0 volts on this side, and our trigger is having 5 volts, and therefore nothing is going to happen until we push this button again. So once we push the button again, this trigger will have 0 volts here. The comparator sets it. We have the output, and while it's on, it's charging this, and the capacitor is providing enough charge for that. So till once the capacitor charges up to 3.3 volts, it's going to set the R latch, which is going to discharge the capacitor again. And this is going to provide a pulse for a short duration of time, which is dependent on the capacitance and the resistor at this point. So we're going to have this kind of pulse. So when you go back to the board and you see this area of the board, you can see our switch here and the timer, and here is the capacitor. So once I push the button, I'm going to see a pulse, and then it's gone. I'm going to push it again, and when you look at what I have here, it looks similar to what I have on the oscilloscope. So when I push the button again, I'm going to see the pulse. So I'm just waiting for this pulse to clear off the screen, and I'm going to push the button again, and you could see it somewhere around here. So I'm going to clear the screen, and I push the button again. And there you have it. So you see the pulse coming back, and it goes back to low, waiting for the next input from the switch. And this is why it's called the mono stable. And the last mode, it's the bistable. So in this case, I'm using the 555 timer as a switch. So I have a switch here, and once I push the switch to this side, this voltage goes to ground, and you have 0 volts here, and sets the latch. The latch stays high, and once I push it back to this point, so once the switch pole connects to this, so it's going to set my reset but part of the SR latch, and it's going to set it back to low. So I'm not really using any of these components on this side of the 555. So you might want to ask, why am I just using this as a switch? Why can't you just plug it directly with the switch with your voltage? And yeah, the reason is because we're going to be using this clock system for a computer, and when you want to debug the computer or perform debugging process, you just want to have one pulse at a time each time you're stepping through your program. And this means, because we're using these switches, they have a lot of bounce when you hit it. So in order to be sure that you have only one pulse each time you press the button. We can use this kind of mode to produce that. So now, because we're going to use this to provide a clocking system for our computer, we are going to have to combine these two. So the astable mode will give us the pulses we require for our computer to run its operation, and the monostable mode is going to provide us with the pulse we need to debug during the debug. So you just want to go step by step to run the computer and make sure that everything's to see if there are issues. And now the question is, how do we combine these two to give us the final clock output? So now I was able to put up this sketch, and this is a logic gate to combine all and get my pulse here. So I have the astable pulse, I have the select pulse, I have the select pulse is the monostable pulse, and the manual pulse is the bistable pulse. So with this logic gate, I'm going to combine these two. Once the select is high, I should get a 1 here, and if the select is high, it means this one should be low. So either of them should give me 1 output from this. And once the select is low, I have this inverter to convert the signal, and then I get a high here. And obviously during this time this would be low, and then I will get my pulse output here. But this would be implemented later. This is the halt signal to stop the computer from running once the computer is done executing the task. And I'm going to implement this much later. So now it means I'm going to need 2 AND gates and 1 OR gate at the moment, but unfortunately I don't have this gate. So, but the beauty of it is you can build any gates with the NAND gates, which is why the NAND gates are referred as the universal gates. And here you have the equivalent of the NAND gate for the OR, and you have the equivalent for the AND gate, you have the equivalent for the NOR gate. So with this I can convert all the gates that I have here. I can convert all the gates that I have here to NAND gates. So I have exactly the same thing, but I'm using NAND gates here. So which means I'm going to use 1, 2, 3, 4, 5. So here's the thing about NAND gates. So when you see here, for example, I have an inverter, and this inverter is replaced with this equivalent with the NAND gate, and you have this AND gate, and is replaced with the AND gate here, NAND gate, and you have the AND gate also. We have the same system of NAND gates combined, and for the OR gates, the OR gate is replaced with this circuit. So if you have a look here again, you will see that my OR gate can be built with this NAND gate combination, which is what I have here as replacement for my OR gates here. So, but if you see, if you're having high here, and this is an inverter, as we can see here. So when you convert from high to low, you're going to convert from low to high again. So which means we don't need these 2 NAND gates, and same is applicable to this point also. Therefore, we only need 1, 2, 3, 4, 5, 6, and 7. So however, Now I've implemented this circuit here using the two NAND gate, and I have my bistable circuit here. As you can see, this is my toggle switch, the one I drew like this. So this is the switch here, so I can switch it to high, I can switch it to low, just as I showed in the drawings. And so I have combined them just like I have here onto the breadboard, and so I'm just going to connect this final output here. So having done that, so now my switch is in the off mode, so which means I can generate single pulse, and I'm going to see my final output at this LED. So when I push, so it means my clock system, it means the clock system is giving me this as my output, and this would be the clock pulse that will be going to my 8-bit computer. So once I push this, it's going to get a pulse and it's going to execute one task. But this I would use during the debugging mode, or when I want to debug a particular program and see how if the computer is executing the task as expected. So but then once I'm done, I can also switch back the computer to its normal operation mode by switching the clock system to the astable mode, and I just have to do that by toggling to switch back. And now the switch is high, and then the output is same as the astable mode. So here the computer is going to run normally with the astable mode pulses. So with this switch, I can switch between the astable mode and the monostable mode to control my PC or my 8-bit computer. So this is just a way to build a clock system for a computer using the 3 various mode for the 555 and combining them with the logic truth table graph, and there you have it. Thank you for watching. See you.